Last time we started taking a look at section 2.2 and we described what sets were. We talked about how to count the number of objects in them, and we said that's called their cardinal number. We talked about one very interesting set, or maybe it's not so interesting, called the null set, a set with nothing in it. And what we're going to start on today is a way to visually think about sets, okay? And so these are called Venn diagrams. I have seen Venn diagrams used personally in my own children's education as young as second grade. They use them a little bit differently than I'm going to show you how to use them, but Venn diagrams are diagrams used to illustrate ideas in logic. A universal set is the set that contains all the elements being considered in the given discussion, and it's actually drawn as a rectangle. Okay? So when we're talking about a universal set, we usually draw a rectangle. Mine looks kind of really skinny right there because that's the little space I've got. And we call it U for universal. A set that is inside of the set, so well, I'll read in the complement. Complement is to given a set F, this is all the elements in the universal set that are not in set F. And it's written F with a line over it. So let me draw the images that this is describing in my rectangle. So my rectangle is the universal set. It contains everything. So like for instance, let's say we had in the universal set your list of all your contacts in your phone. Okay, that's the universal set. And then we have a smaller collection of those things, and this smaller collection are those that you really like talk to a lot or text a lot. You communicate with them frequently. We all have those, right? And so this would be set F, and it's usually drawn as a circle. Mine looks like an oval because, you know, I'm out of space, but usually draw them kind of circular shaped inside. And then the complement would be everything outside of the set. So everything I'm highlighting in yellow would be considered F complement. Okay, it's all the yellow stuff. And this would be everybody in your phone that you don't correspond with frequently. Right? So you've got to be able to differentiate those categories to be considered complements. Just for your reference, because other books do other things, there are two other common ways to write complements depending on the resources that you're using. One of them is to write a little C after the set's name, FC for F complement. And another one is to write an F with looks like an accent mark or kind of like an apostrophe or a hash mark, or prime is what we call it when we're talking mathematics a lot of time. So we would have F complement written that way. So these are alternate notations. Our book uses the bar on the top. Okay. All right, so we're going to do an example. U is the universal set of all the students at OBU. A is the set of those who are graduating. Describe the complement of A. What would A complement be in words? Yeah, it's all OBU students not graduating. Does that make sense? So you guys should be able to think just off the top of your head of lots of things like this. So let's say, for instance, we took the collection of all of the people in your family as the universal set. Everybody that you would say, I'm related to that person, okay? And then you have a smaller collection inside that you would consider your immediate family. It's probably the people that you sort of grew up in the same house with. That would be considered your immediate family. Then all of the people on the outside of the circle, the complement, would be your extended family. That's how we would describe that. You could do the same thing with this example with boys versus girls. Not versus, but, you know, comparatively, right? So we could do all OBU students, the circle inside's the girls, the complement would be the boys. So we can create these kind of as long as we like from different sets. Now a subset looks like the following. If you have sets A and B, we would say that B is a subset of A if and only if every element of B is an element of A. And it's written like this. You write B, And it kind of looks like a U on its side, or a sort of elongated C with a line underneath it. B is a subset of A. Okay, so again, let me draw a visual for our Venn diagrams here. We have our set A, and in order to draw a subset, it means there's a smaller circle inside of A. So here's A, and here is B, and this is my universal set. Sorry, I should have drawn my diagram a little bit bigger up at the top, but that's what I got. So let's look back at the definition and see if we can sort of make sense of the pieces. B is a subset of A if and only if every element of B is an element of A. So is the entire circle B, everything that is contained inside of the circle P, also inside of my circle A on my picture? It is. So this diagram fits this description. So if we were looking at subsets we'll use this one over here that we just did. Let's say that we said we have set A is all the seniors who are all the people who are graduating, right? And let's call set B, whoops, B, not B complement, B, the girls that are graduating. Now, the question I'm asking you is this set B inside of A? Are the girls that are graduating contained inside? Are they a part of the set, all the students that are graduating? They are. So this would have this relationship. All the girls that are graduating is a set that is inside of the set that's everybody that's graduating. It's just a smaller collection. Now, I say smaller collection because that's usually what we deal with, all right? But technically, it could be the same size. So we could say, this would be funny to say, but in my family, myself, my husband, we don't have any other children besides the children we share, okay? So if I talk about my children and my husband talks about his children, we're talking about the same set of kids, okay? Everybody's talking about the same set of kids. But by definition, one would be a subset of the other because all of my kids are his kids and all of his kids are my kids. So definitionally, they're subsets. My kids are a subset of his kids. Okay? But they're not a proper subset. A proper subset is a subset, and it's actually smaller, for sure smaller. It's not just maybe smaller, it's for sure smaller. So I have brother-in-law and sister-in-law. My brother-in-law had a daughter already before he married his wife now, and then they had 3 kids together. So if they talk about their biological children, her biological children is a subset of his biological children because he's got one more than she does. Okay, that's a proper subset. It's a subset, but it's also a proper subset because it really is smaller than the other set. If my husband and I have that discussion, it doesn't work like that, right? Because we don't have any extra kids between the two of us or outside of the two of us. So those are not proper subsets. So how do you test if something's a proper subset? Well, first of all, you got to make sure it's a subset. That's what this says, right? If and only if it's a subset. That's the first thing. And then the second thing is that there's at least one element in A, the bigger set, that's not in the smaller set. Like it's legitimately smaller, the one that's on the inside. They're not just renaming the same group of kids like I just did when my husband and I had that conversation in my head out loud for you. So, How do you count subsets? Well, if you have n elements in the set, then there are 2 to the n subsets. And if you remove the one that's actually equal to the set itself, then there's one less, 2 to the n minus 1 proper subsets. And I'm going to do an example of that next, I think. Yep, example 5. All right, we're going to consider the set of all mathematics faculty members at OBU. Just so you know, in case you didn't, there are 5 of us. And the question wants to know how many different subsets are there of the math faculty. Well, we're going to do this by the number of sets formula that I got to below. But then I'm going to talk to you about what those actually look like, so that if you were thinking like, okay, but what are those? How does there so many? Because it feels like there's a lot. We can see about how that works. Okay, so there's 5 faculty members. So there would be 2 to the 5 subsets And either off the top of your head or in your calculator, what is 2 to the 5? 2 to the 5th? 32 is right. There are 32 subsets. How many different proper subsets? What should that be? 31, just one less. I teach an online contemporary math class, and this is actually inside of the material that they just learned. And so they get partial credit if they can at least remember this. Even if they screwed up part A, if they got one less for part B, that's partial credit, because it's always that relationship. So let me talk to you about how those subsets are created, because I mean, it's all well and good to give you formulas. I mean, we can do that, and you've probably had plenty of math teachers who've done that, but they don't really mean a lot to you, and you don't really understand how they're working if you can't see where they're coming from. Okay? So one way of getting a subset is that we could think about having, a collection of 5 people, and you're making a committee. Okay? And let's say the committee has 2 people on it. Well, I'm going to use the letters A, B, C, D, E, just so that I have a reference point for writing them down, okay? So we could have a committee with A and B. We could have a committee with A and C, or A and D, or A and E. Correct? That's already 5 different subsets. What else could I have that are 2 people on them? What have I missed so far? BC, BD, and BE. What else have I missed? CD, CE, and there's one more, DE. Okay, this kind of feels like when we were counting something else. Do you remember what we did? We did a problem like this. It was the second day of class where we wrote something down quite similar to this. Do you remember what it was? Very good. It was how many games to schedule when we had soccer teams playing. Do you remember that problem? And I said, oh, okay, we don't want to reverse the numbers or the letters around because that double counts things. Same thing here. Okay, this would be if I had 2 people on a committee. But did it say I have to have 2? Well, no. I mean, a smaller collection, a subset, would also potentially have 3 people on it. Okay, so this is getting 2 people on it. I could have 3 people come on it. I could have A, B, C, or A, B, D, or A, B, E. Or A, C, D, or A, C, E, or A, D, E. Dot, dot, dot. There's a whole bunch more. Okay, there's more. But it might not just have 3 people on it. I could have a smaller group that actually has 4 people on it, right? So I have my groups of 4. I could have, basically, just the question is who gets left out, right? In this group, E got left out. In this group, C got left out. We could write them all down. I have no intention of writing all these guys down. I'm just trying to give you a feel for what's going on. Are you guys good with that? I don't want to write down 32 of them. But I could have a collection, not a collection, but I could have a subset that has everybody in it. Technically, that's a subset. Not a real exciting one since it's the whole group itself, but it's technically a subset by the definition. I could have a subset that's the empty set. I could talk about the math faculty members that currently live in Great Britain. None of us do, so that would be the empty set, right? And we could talk about that. It would be a weird thing to talk about. We could talk about having subsets that are just one person at a time. Subset with just person A in it. Just person B, C, D, or E. So we have all these different subsets. There's 32 of them. If we eliminate this one, that gives us all the proper subsets. And you can see very quickly why having 5 elements just blossoms very quickly into 32 different subsets. So just imagine what happens if you had 10 elements, right? 2 to the 10. It's a very large number. The numbers get big very quickly because they're exponential. All right, let's take a question in reverse. Suppose you have a set, and you know there are 63 proper subsets. How many elements would there be in the set? Somebody said 64 would be the number of proper, so it's 63. Hang on, that's not what I wanted. I'm going to write down what you said because it fits with the description. There's 63 proper subsets. There are 64 subsets. Yep. How can I find the number of elements in the set, though? You're close.
2 to the power of what equals 64?
We want to figure out what the exponent would have to be. So you're thinking about if I knew the exponent, but I don't know the exponent, I know the base. So I can't square root it. But I do need to know what number, when I raise 2 to what number do I get 64? And your calculator can do that. Try some, right? You know it's not 2 to the 5th because that was 32. So what is it? It's 6. There are 6 elements in my set. So as soon as I have 6 elements, I will have 63 proper subsets. And I really don't want to write down 63 subsets. Okay? But it'd be the collection, right, of nobody in the set, 1 person in the set, 2 people in the set, all the way up to all 6 people or elements in the set. All right, we're going to take a look at some fill-in-the-blank kind of statements. This one wants us to indicate which symbol, and it gives us 2 options, would make the statement true. So let's remind ourselves from last time, because it's probably been 48 hours or more since you looked at those 2 symbols. What do each of those mean? Good. Is an element of and is not an element of. And elements are just items that are in the set, okay? So let's take a look. The first one, what is this saying on the left-hand side? Okay. But what is that thing? It's a, what kind of set? It's an empty set. So the first thing I want to tell you is that this is not an element of it. And here's why. The empty set is a set. It's not an element to begin with. So the first thing is you have to figure out is it even an element? I can't even talk about it being an element of something else if it's not even an element. And this one's not. It's a set. That item on the left is a set. Now, this is an element. I mean, 15 is an element. And the reason I know it's an element is actually because it doesn't have curly braces around it. That's how I know. It's an element because it doesn't have curly braces around it. So it is an element. Now we just have to figure out if it's an element of what comes next. Is it an element of that stuff that comes next? So let's figure out what we have over here. This says, in its set builder notation, we have all x such that x is equal to 2n, and n is a natural number. So let's start here. N is a natural number means what values does n have? Okay, it's all the numbers in 1, 2, 3, and so forth. So if I take those numbers and I plug them in one at a time into the equation 2n, what kind of answers do I get out of it? Somebody said 2. If I plug in n equal to 1, I get 2. 4. 6. Okay. So this is a collection of even numbers. That's what I have. What is written on the right is a way of writing even numbers. And the question now back to what was had is 15 an element of the even numbers? And no, it is not. It's not an element. Okay, C. Is that a set or is it an element? It's a set, which means it doesn't matter what comes next. It's not going to work because it's not an element to begin with. Okay, so don't overanalyze things. Look at what's really written there. Make sure you understand it. 16, is it an element or is it a set? It's an element. How do you know? No curly braces, right? No curly braces around it. So it's an element. What do we have over here on the right? That would be a listing method or a roster method of the even numbers, exactly. So is 16 an element of the even numbers? Yay, we finally get to use the element symbol instead of the not an element symbol. Okay, you ready to do the next set? They're similar. In fact, if you take a look, some of the numbers, some of the equations and so forth, in fact, all of them, are the same. But the directions have changed. We're not using element or not an element. What are these symbols? What is the first one? We actually talked about that one. We haven't talked about the second one. What's the first symbol mean? It's a subset. So this symbol is subset symbol. Now, we didn't talk about it, but I have full confidence that you know what that other symbol is. Yeah, it's not a subset. Okay, so let's look first and make that same argument we did on the previous slide. Does the item that's on the left fit into the category of set or element? If it's a set, it might be a subset. If it's an element, there's no way it can be a subset because it's not a set to begin with. So, is the first one, is that a set? Yes, it's an empty set. That is the description. Remember, we had another symbol that looked like this where we just wrote nothing inside of it? It's the empty set or the null set. It is a set. Then the question is it a subset of what comes next? This one's a really weird one, so I wanted to make sure to do it with you. So let's go back to the definition of subset to decide if it actually works. The definition would say the null set. Is the null set a subset of A? And it is if every element of the null set is an element of A. Is every element of the null set an element of the set with 0 in it? Feels weird to ask, but it is, because there's nothing in the null set to have to see if it's inside of it. So you get it sort of by default. It is in fact a subset because everything in the null set is inside the set with 0 in it. Now, you might write yourself a note that says something like this. The empty set is a subset of every set. In fact, when I was writing out, I didn't write all of them, but when I was writing out some of these items that are the subsets over here, did you see I wrote one that said empty set? Yeah. Right. There's a possibility that if I'm creating committees and so forth of all my faculty members and such, that I try to create a committee of everybody that lives in Great Britain and we have nobody in it. That's a subset. Not a very exciting one since nobody's in it, but it is. All right, part B. Is this an element or a set? It's an element. And if it's an element, then it cannot be a subset. That's it. All right, how about over here? Element or set? Set. So it stands a chance. It might be a subset because it's at least already a set. So now let's look at the items on the right. I have a set that contains the number 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5, which is a funny way of writing what numbers? 3, 4, 5, and 6. That's another alternate way of writing the same collection of objects. Is the subset that contains the number 4 a subset of the number of the set that contains 3, 4, 5, 6? Yes, because everything in the set that contains 4, which there's just one thing, it's the number 4, right? 4 is the only thing there. That element 4 is in the other set. So this is a subset. If you imagined drawing a Venn diagram for this and sort of putting the numbers sort of where they belong, right? You'd have one circle in the middle and all it would have in it is 4. And then 5 and 6 and 3 would be out here, right? Everything in the big circle is 3, 4, 5, and 6, but in the little circle is just the number 4. Ariel.
So if it's not a subset, but for D there, 16 wouldn't be a subset.
Correct.
Right?
Mhm.
So that it has no chance.
Right. 16 is not a set anyway, so it can't be a subset.
Right.
You got it. Yeah, so there's two things looking at. First, is it an element or is it a set? In either of these examples, right? Is it an element or is it a set? And then, does it fit into the description of what's on the other side?
Can they give you like a, so like for this, could they put like 4, 5, 6 in that and ask if this is no subset?
Sure. Yeah, so could you have a collection that said 4, 5, 6? And, oops, I didn't mean that.
So it doesn't have to be one number?
Does not just have to be one number. And then we have the same thing over here. Sure, absolutely. Yep. Any other questions? Okay, I referenced this principle last time in class when we were talking about correspondences, one-to-one correspondences, and I talked about pairing up people in my family and people in my husband's brother's family, and we have the one-to-one correspondence because there's the same number of people. And we use the fundamental principle of counting when we multiply the facts together. So let's take a look at this. It says, if an event capital M can occur in little m ways, an event capital N can occur in little n ways, then event M followed by event N can occur in m times n ways. All that it's saying is that when you count the different objects involved, you multiply their sums together. So we're going to do an example with clothes because that's a good one to do. How many different outfits, either ignoring that they may not match or saying that they just all do, how many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? So we did one with lines when we were looking before. Do you remember that? Put lines down. And they were correspondences, so they kind of represented something a little bit different. But here, basically, this is my shirt line, and this is my, did I call them pants? Skirts. That's what I've got in this one, skirts. And I've got shoes. So how many shirts do I have? 3. How many skirts? And how many shoes? 5. And the fundamental principle of counting says I just multiply those possibilities together, and that will give me the total number of possible outcomes for outfits that I have. And what would I get if I multiply 3, 4, and 5? There are 60 outfits. Do we have any fans of Sonic in here? Anybody like the Sonic drinks, the flavor add-ins and things like that? They used to have it on their signs. I don't know if they do anymore. I haven't seen it myself recently. But they used to talk about how many flavor combinations that you could make. This is the kind of argument they were doing. They have the total number of, soda options, the total number of tea options, whatever, and then, so the total number of like their base drink, and then you've got your total number of flavor add-ins, and you've got to figure out what happens if somebody adds in 2 flavors, because that's what I like to do at Sonic, is add in 2 flavors, and you have all these different combinations, and you come up with a very, very large number pretty quickly when you consider there's really not that many individual choices to be made. But it's from the fundamental principle of counting that they use their argument. Here's to another one, same principle at play here. You have 6 favorite stores in the mall. In how many ways can the following happen? You have time, on part A, to only go to 3 of them. Well, if you only have time to go to 3, you'd have 3 lines. Okay? So how many choices do you have for the first store you go to? 6 choices. Just like when we did our skirts, we had 3 different choices of shirts, rather, that we could choose. We have 6 different stores we could choose. Once I've chosen a store, though, and I'm going to store number 2, how many store options do I have there? 5. There are 5 choices left. So this one has a diminishing process to it, right? And then after I've gone to those first 2 stores, it would seem unlikely I would go back to store number 1 or stay at store number 2. So I have how many choices left? 4. And the fundamental principle of counting says I can multiply those results to find out how many different groups of stores I could go to, how many different outcomes could happen, and what do I have? 120. Now what if you have time to go to all 6 of them? Well, we're talking about the ways in which you go to them. Now, the reality is most of us do some sort of thing when we're shopping or when we're going around town or whatever. We try to minimize the driving back and forth stuff we do. So we're not trying to minimize that in this particular argument. We're just trying to find the total number of possibilities. So if I'm going to store number 1 and distance is not an object, I have 6 options when I go to the first store. And I'm going to all 6 stores, so I need 6 lines. So the second option, I would have how many options, or second store I go to, how many options? 5, and then, exactly. And it would decrease until I get to my 1, and if I go back and I multiply them, how many different ways could I go to my favorite 6 stores? Yep, 720. All right, last example for today. This is your opportunity to write down something about your life. I won't make you read it, but I will ask for volunteers if you want to volunteer. I want you to create a real life example of a null set in your life. Okay, I will give you an example for mine. We're going to go with lizards today. The lizards living in my house. So if I tell you that's a null set, what does that mean? There are no lizards living in my house. Okay? So I want you to write one down. Write down a null set that applies to your life. Don't use my example, and it doesn't have to look anything like my example. All right, would somebody share with us what you have for your null set?
Boyfriend.
That comes up every time I teach this class.
It's Valentine's
The
Day.
number of boyfriends in Hannah's life. That would be a null set apparently at the moment. What else do we have? And I shouldn't say the number of, but the boyfriends. Number of would be counting them.
Children.
Children for Taryn at the moment. Null set. It's easier to finish college if you don't have them.
Yeah,
Says someone who had one when I was almost finished, but still, yeah.
My family members in
All right, so family members
in Oklahoma.
in Oklahoma. Okay, family members living in Oklahoma. We'll do one more if somebody else has one more you want to share. All right, we'll stop there then.